Okay, we're going to generate an equation for dealing with standing waves on strings. So what we're going to need to do is we're going to want to draw the first, second, third, and fourth harmonics and see if we can identify a pattern. But before we can draw what these shapes are, we're maybe going to want to see them on a spring. So let's go look and see them on a spring. Okay. So we're going to look at how a wave travels on this slinky. So as I make a disruption, and this is going to be a transverse wave, so I'm going to make my disruption so it's perpendicular to the direction of motion, that wave travels down and reflects back. And it reflects back and forth, but it does lose some energy each time. If I send a longitudinal wave, so that's where my disturbance is parallel to the direction of motion, it looks like this and it does something similar. Okay? But what I want to look at is what happens when I send multiple waves. So I send one and then I send another. What happens when those waves meet? Okay, so I want you to watch carefully when they meet. They overlap one another and they increase the overall amplitude. And what will happen is eventually we can get something called a standing wave. If I have a frequency that matches this length and this speed well, we can get a standing wave. Now what we're going to look at next is how that would look if I have a faster speed. All right, you can all right, so now you can see that we have a different spring. This one has a little more tension in it, so the wave is going to travel faster. And so again, if I have a low frequency, I can hit this first harmonic. And this is the way most strings will vibrate in, say, a musical instrument. But they can also vibrate if you put in a higher frequency to this. We can vibrate at what we'd call the second harmonic. Okay. And you see this place here where it's going a lot, that's where the wave bouncing back is meeting the wave going in and we're getting constructive interference. The spot in the middle that doesn't look like it's moving much, we're getting complete destructive interference. Meaning the wave going down this side is on there and the wave going down that side is here, and so they're canceling one another out. And if I keep increasing the frequency, we can get the third harmonic. And if I keep increasing the frequency, I can get the fourth harmonic, and so on. All right, let's take a look at the board again. All right, now we've seen those harmonics on the spring. We've seen those locations of destructive interference, those locations of constructive interference. So let's go ahead and draw it on the board and identify what some of these points are. So our first harmonic was our fundamental frequency. This is the lowest frequency that I can get a standing wave. The second harmonic looked like this. And when we draw these, we're going to go ahead and we're going to draw one solid line. So that represents where that spring was at its maximum. And then we're going to draw a dashed line, and that's when it reaches the other maximum. And it just kind of oscillates back and forth between those two. And so here's our third harmonic. And then lastly, we'll draw our fourth harmonic here. Now, one way you can count the harmonic is you can count essentially the number of humps. So there's one hump for the first harmonic, two humps for the second one, three for the third, and so on. Now, some of the points that we want to be able to determine is I want to be able to talk about this place where we have that complete destructive interference. Complete destructive interference at this point, and that point is called the node. These points where there is that most constructive interference, we call that an antinode. So this is our picture. So now I want to see if there's a pattern. And the pattern I'm going to look for is a relationship between the length, the wavelength of this. So as I go up in harmonic number, how does that change? So L is going to equal some fraction of a wavelength. So a full wavelength would start here and end right back there. So this was our full wavelength. So 2 humps equals a full wavelength. So 1 hump would be a half a wavelength. So I have half a wavelength. This one has 3, so that would be 3 halves of a wavelength. Now the question is, are we seeing a pattern? So each time I go up a harmonic, it goes up by a half of wavelength. So my last one is L is equal to 4/2 of a wavelength. Now, why is it important to look for a pattern? And so this is going to give us a relationship between our wavelength, our length, and our harmonic number. And so what I'll do is I'll go ahead and I'll put all this together, and I'll be able to say L is equal to N over 2 times lambda. Now I'm going to make some substitutions here. I'm going to use the equation that velocity is equal to frequency times wavelength. So wavelength is equal to velocity over frequency. I'm going to go ahead and substitute this in here. And so now I have length is equal to NV over 2F. And I'm just going to multiply F to both sides and divide the L over. So I'm solving for frequency. So frequency is now NV over 2L. And I'm just going to clarify what N is here. N is the harmonic number. So it's going to be numbers like 1, 2, 3, and so on. Now, a secondary thing that kind of works out interesting here is if I plug in 1, if I plug in N equals 1, the fundamental frequency is going to be whatever V over 2L is. So that's going to be equal to the fundamental frequency when N equals 1. And so what I can say is that the nth frequency is equal to N, and instead of saying V over 2L, I can say it's the fundamental frequency. Meaning, if the fundamental frequency is 200 hertz, the second harmonic is going to be 400 hertz. The third harmonic is going to be 600 hertz, and so on. Right. So these harmonics are gotten by adjusting the input frequency. Now, in some instances, you don't really get a chance to adjust the input frequency. An example would be a guitar or, say, this musical demonstration device where I just pluck it. And when I pluck it, there is a frequency that's emitted. And it has to do with the velocity and the length. Now, what I can do is I can change some parts of this. I can change, say, the tension by adjusting these knobs. I can change the length by adjusting where I put my kind of, bridge. So what I'm going to have you do is I'm going to have you come in a little closer and we're going to go through like how I can make multiple harmonics on the same string. So come on in. All right, we're going to look at for a second how this affects musical instruments. So when we want to change the frequency on a musical instrument, we do have a couple options. We can adjust the length of the string by placing frets on it. We can also adjust the tension. So those are two ways we can adjust the frequency. And by adjusting the tension, we're adjusting the speed. Now, on any given string, when you're doing it and you pluck it, you can only put in a pluck. You're not putting in a frequency like we did on that spring. So how do you know how to get the second harmonic on one of these strings? Now when I pluck down here, maybe I'll get more of the second harmonic and less of the first, but it's typically dominated by the first, but there's a mixture of the other ones. And now I just want to show you how those harmonics play. Now remember, if the first harmonic is, say, 400, the second harmonic should be 800, and the third should be 12. And so what I can do to kind of force that second harmonic is I can kind of dampen out that first harmonic. So I really want it to vibrate here and here. So let me just flip this around here. So I'm going to dampen it in the middle. I'm going to pluck it down here. And I'm going to get that second harmonic. Or I'm maybe go for the third harmonic. Maybe the fourth even. Okay. And you can see how it got louder or higher and higher frequency as we went higher in the harmonics. All right, back to the questions. So we just saw how we got different harmonics on that string. We saw how two different strings of the same length can produce the same frequency. And so we have this equation here that relates the speed of that wave on that string is equal to the the square root of the tension in the string divided by the linear mass density. And so linear mass density, mu, is found by taking the mass of the string dividing by the length of string you have. All right, so let's go ahead and change gears and go back to what we originally started with. this equation that relates the frequency, the harmonic number, the speed of the wave, and the length. And let's try an example problem. So I have a 6 hertz standing wave here. It's occurring on a 3 meter long spring. And I want to go ahead and I want to find out how fast is that wave actually traveling? How fast is that energy traveling back and forth on that wave? So in order to do that, I am going to need one more piece of information before I can use my equation. I need to know, what harmonic is this? What is this 6 hertz harmonic? And so thinking back, the number of humps told me about the harmonic number. So this would be a first, second, third, fourth, fifth harmonic. So I know n is equal to 5. And so I start plugging in my equation. So I have f, the fifth harmonic, is equal to nv over 2l. We can plug in our numbers. So I have 6 is equal to 5 times the v divided by 2 times the length, which was 3 meters. And so at this point, I can go ahead and solve for v. So 2 times 3 is 6. Multiply it over, I get 36. Divide by 5. And I get 7 and change. So I get 7.16. So I'll just round it to 7.2 meters per second for the speed of that wave.